We previously looked at explosions in terms of Newton's third law. For every action, there's an equal and opposite reaction. The force of cart 1 on cart 2 is equal and opposite to the force of cart 2 on cart 1. They explode because a spring-loaded plunger releases between them. Newton's third law leads us to the law of conservation of momentum. If we consider the force of cart 1 on cart 2 is equal and opposite to the force of cart 2 on cart 1, and then we multiply each force by the time of the explosion, force times time gives us the impulse. And we know that an impulse gives rise to a change in momentum. So what we have is the change in momentum of cart 1 happens to be equal to the change in momentum of cart 2. If the masses of the carts are equal, then the change in the velocity of the carts will be equal to. We can extend the derivation we started earlier to come up with the full law of conservation of momentum. First, we take our change in velocity and break it into the final velocity minus the original velocity. Then we can distribute the mass, so we come up with 4 individual terms of mass times velocity. This is the momentum of each cart before and after the collision. Then we can move the terms from one side to the other. Solving the algebra, we wind up with the final situation of cart 1 and cart 2 on the left-hand side of our equation, and the original before the explosion on the right-hand side of our equation. And then we substitute mv with the term p for momentum, and thus we have the law of conservation of momentum. But what if the masses of the carts are not equal? Then the velocity of the carts will not be equal either. We can calculate the final speed of these carts in the video you just saw. One cart had 2 extra bricks, so it was 1,500 grams. The other was 500 grams. They both started from rest. Suppose the cart with only 500 grams is moving at 12 meters per second. How fast is the other cart moving? Well, using the law of conservation of momentum, first we cross out the 2 terms because their velocity is 0, and we equate the velocities, move the masses to one side, and we find that the heavier cart will actually move 3 times slower than the fast cart, and 3 times slower than 12 meters per second, gives us 4 meters per second. What if this explosion was moving? If we look at this quick video, we can see the same plunger experiment in motion. And we can see that one of the carts apparently seems to stop, but the other one seems to go away twice as fast as the stationary situation. Now, what if the masses of the carts were unequal with an explosion like this? We'll have a workbook problem on a skateboard similar to this. We've got 2 objects moving along, one heavier than the other, and we see that one goes flying backwards and the other goes flying forward. Let's solve this problem. Suppose the light cart is 500 grams and the heavy cart is 1,500 grams. Both carts start at 4 meters per second. The light cart flies backwards at 2 meters per second. How fast does the heavy cart move forward? Again, we start with our law of conservation of momentum, writing down terms for each cart. Unlike the other explosions, this time they don't zero out, but look, because they're moving at the same speed, we can actually factor out the original velocity. Remember, always solve this problem using the algebra first. Do not plug in your numbers until the very end of the equation. So we isolate the final velocity, and then we plug in our numbers. We have 4 meters per second for the original velocity. The other cart moves backwards at 2 meters per second. And of course, we're dividing by the mass of that heavy cart. And lo and behold, the final velocity that we wind up with is thus.